Yeah, so good evening. So we'll wait for 1 or 2 minutes. Then we'll start with the week 7 session. So, welcome to the live session on fundamentals of combustion course. So, this is a week 7 session. So, this is a 2-hour session. So, first 1 hour I will try to briefly cover what has been covered in the week 7. And in the second hour, we will try to solve some of the questions which will help you in solving the assignment. So, we will begin with our session today. So, in week 7, we are mainly focusing on the different types of combustion processes involved, and we are mainly focusing on characteristics of the combustion flame and detonation and laminar pre-mixed flames. So we are dealing the fundamentals of the laminar pre-mixed flames and combustion flames and detonation. Basic idea was taught to you in your week 7 videos. So I will just briefly cover what was taught, and then we will move on to the questions that we have. So, the main topic that was introduced to you here was something called premixed combustion. So, in a premixed combustion, you consider you have a reactant mixture, which consists of your fuel and oxidizer. And these are thoroughly premixed and they are present inside the combustion chamber. So they are thoroughly premixed. So before the combustion process happens, they are thoroughly premixed and they are sent into the combustion chamber. So based on the size and configuration of the combustion chamber, a volumetric reaction. So you have a volume, so you have different fuel and oxidizer present in the system, and a volumetric reaction occurs over the entire chamber, and we consider that it occurs over the entire chamber simultaneously. So that is one difference that you will see from the mesh things that we are seeing. And we consider that the properties are uniform and they change with time. And these volumetric reactions occur in a small constant volume chambers. So there are different methods we use to see the kinetics on this. So we use something like bomb calorimeters, which are like a large scale constant pressure chambers, or we use something called well stir reactors, and then we have something called plug flow reactors. So these are different reactors, and these reactors are usually, we call it as homogeneous reactors, where we try to have the conditions that I mentioned here, consider them throughout uniform. And the intensity of the reaction and the speed with which the chain reaction takes place, it all depends on the boundary conditions that you have. So the speed and intensity of reaction, it depends on, one is the boundary conditions that you have, and then the composition of the reactant mixture, then it depends on the pressure, it depends on the temperature inside the combustion chamber. So these reactions, so one common thing that common simple example that was shown to you was you have a piston with you and you have your volume present here. So this is a constant pressure system where you have your temperature as a function of time, your mass fraction as a function of time, and your volume changes with fraction of time. Whereas in another case where you have a constant volume system, here you have temperature changes with time, your mass fraction changes with time, and your pressure changes with time here. So that's the one difference here. And then you have something called well-stilled reactors, where you have your reactants and you have your products going out. So in a well-stilled reactor is a steady state condition. It is a steady state where steady flow control volume, where you have steady flow control volume is present, with your temperature is constant, your mass fraction and your pressure is all considered to be constant in this particular system. So that's the main difference. And said that, then you were introduced to one more terminology called auto ignition. So by the term you can see there is an ignition that is happening by itself. So when you are having a fuel air mixture or a fuel oxidizer mixture in flammable proportions with sufficient enough fuel and oxidizer, if it is injected into say a small spherical chamber, say you have, and this is the chamber and you have your fuel plus air or oxygen being introduced into this particular system, and the chamber temperature at which so you have your pressure regulators here and you have your temperature thermocouples measuring your chamber temperatures, and so the temperature, say we measure as Tc, the chamber temperature at which there is a rapid rise, in pressure, or so a rapid rise in pressure is what you usually refer as explosion, which occurs. This can be estimated by continuous monitoring of the pressure inside the chamber. So you have pressure sensors that can measure your pressures within the chamber. So that particular temperature at which you have a sudden rise in temperature. So you might remember the diagram that was shown between pressure and temperature at the time. So as time progresses, you will be slowly, gradually increasing within your chamber. But there will be certain point, Tc, where you abruptly increase your pressure to a very high value. So we say the system explodes, goes to an explosion state from this particular point DC. So the temperature of the chamber at which the sharp pressure rise occurs is what we call as the, so this is what we call as critical or the auto ignition temperature. So I hope that is clear. So now so once we know there is an auto ignition temperature for systems, now so this is the critical or the point where this happens is what we refer to as explosion happening. So for a given fuel oxidizer mixture at an initial pressure, say given just after filling your tank, whatever the pressure you have, reactants of into the chamber, the temperature of the chamber, so in order to find these explosion limits, what we do, the experiments what we will do is we will have a fuel oxidizer mixture at an initial pressure. So you have an initial pressure at which your fuel and oxidizer is sent into the chamber. Then the temperature of the chamber is varied. So you have a chamber, you have your reactants going at a given pressure, and you have a measure where you can change the temperature from which is Ti, and the temperature of the chamber is varied. So you vary the Ti slowly according to your requirement. Now the critical temperature at which the ignition and a subsequent rapid pressure rise occurs is recorded. So your pressure rise is recorded here. So we change the temperature slowly and we record the pressure and for each conditions, and the temperature corresponding to where you have a rapid rise in pressure is what we call as the explosion. So the critical temperature, or the auto ignition point, sorry, so there was a network issue. So now we say that the critical temperature of the auto ignition point, or the auto ignition temperature point I should say, the temperature point is also what we refer to as the explosion limit. So the value, so its value varies with initial pressure. So the explosion limit, it depends on the initial pressure that you have, that depends on the amount of reactants and the properties of the, and then it depends on the properties of initial reactant mixture that you have. It depends on the properties of initial reactant mixture that you have. So then in order to do this, you need to do your experiments are repeated for different field pressures, the inlet pressures that you have, and the results are plotted for a pressure temperature curve. So PT curve is plotted, and which is used to identify the ignition, auto ignition or the explosion limits for different reactant mixtures that you have. Now a standard one that you need to be remembering is the explosion limits of stoichiometric hydrogen and oxygen mixture. So if you see the stoichiometric hydrogen oxygen mixture, I'm sure you might have seen this in your videos, where you have your x-axis as your pressure in mm of mercury, and your z-axis, x-axis you have your temperature in degrees Celsius, and you had different points and you were focusing on one particular temperature that was close to 500 degrees centigrade, and you had your pressures say 0, 10. So maybe first I will draw the inverted S curve that you have seen in your lecture. So this was close to 1.5, and then you have this particular close to 50. So here you had 100, and here you have 1000, and maybe above that is 10,000. So you have 3 different points here. So one you had here, one you have here, and you have here one. Now, so this was your first limit, and this was your second limit, and this was your third limit that you have. And if you see the region of explosion, so if you see, this was the region that you had for explosion region, this was, and your non-explosion region, this particular region from 2 to 3, here it was your non-explosion region. So now, throughout the video you might have seen the different conditions or different ways why we are considering this and how this is happening. So if we say in brief, the temperature and pressure corresponding to initial charging conditions are plotted, where explosion limits are explained by considering the temperature and pressure dependencies of elementary reactions. So that's one thing. So here the kinetics plays the dominant role. So you need to consider the elementary reactions here, and taking a temperature of 500 degrees centigrade is what we are looking here. So for the lowest temperature of say 1 up to 1 mm mercury, to 1 to 1.5 mm of mercury, if that is what you are seeing here, there is no explosion occurring. So there is no pressure rise there that you see there. Now for at very low pressures, so what happens is like, so at this particular points, what happens is you have very low pressure, and so your free radicals are produced. So your free radicals are produced. They are produced by the reaction H2 plus O2 giving rise to HO2 plus H, where HO2 is your metastable species that I hope that you. And then you had reactions like chain sequence reactions like H plus O2 gives rise to O plus OH, and then you have H2 plus OH giving rise to H2O plus H. So here you can see that these radicals are produced, but they are being destroyed. they are being destroyed near the walls of the vessels. They have been destroyed near the walls of the vessels, and wall reactions are not gas-phase reactions. So radicals, they just diffuse into the walls, and so eventually your pressure is not rising up anymore. Now when your pressure, say I'll use another color here. So now when your pressure is above 1.5 mm, so this region is what now we are looking into. So when your pressure is above 1.5 mm, the mixture ignites and explodes. The mixture that you have, it ignites and explodes. Now at the sufficient value, so now you are having sufficient value of pressure, the chain sequence reactions, the chain sequence reactions that you have, they dominate over the destruction of radicals that you saw from the walls. That was the case when at the below the first limit that you have radicals at the wall. Now increasing the pressure results in an increase in the radical concentration, and the reaction rate increases non-linearly. So this continues up to, say, to the point where you have here 50 mm of mercury that you have. So up to that your explosion region goes, and now when you move on to the next region, maybe we'll use a more stronger one. So if you are considering this particular region, so if you take this, when your pressure is way greater than 50 mm of mercury that you have, so the mixture becomes non-explosive due to the mixture becomes non-explosive. And so why this is due to the competition of H atoms between the chain branching reactions. Like you have H plus O2 plus the metastable dummy thing that will give rise to metastable plus M. Here this HO2 is being a metastable species, becomes non-reactive under these pressure conditions. This metastable species becomes non-reactive. So now at the third limit, that is when your pressure is above this particular region. So now we are considering region above this. Now when we are considering this particular region, so at the third limit, where your pressure is around greater than 3000 mm of mercury, the chain branching reaction. So you had the reaction like HO2 plus H2 giving rise to H2O2 hydrogen peroxide plus H. This creates hydrogen peroxide sequence, and the system again becomes explosive. So if you observe here, so this was the temperature, say close to 400 degrees centigrade. When temperature is less than 400 degrees centigrade, there is no, so if you see this region, there is no explosion for any particular pressure value, be less than 4, for less than 400 degrees, and for greater than 500 degrees, 580 degrees centigrade, there is this region. the explosion occurs irrespective of the pressure. Whatever be your value, the explosion will occur. So that was one of the important explosion diagram, that pressure temperature diagrams that you need to remember. And said that, then you were introduced into the explosion limits of hydrocarbons. So then you were introduced into the explosion limits of hydrocarbons. So if you remember, you had a plot where you show this as this was your methane, then you had ethane having certain this kind of plot, and as your hydrocarbon values were increasing, you see there is a tip over the region which was different from the regular hydrocarbons that you had. So this happened within a region of say 300 to 400 degrees centigrade, and you had your pressure and temperature in degrees centigrade over here. So this higher hydrocarbons, C3H8, propane and all, when we are doing. So hydrocarbon fuels, they exhibit single and two-stage auto-ignition process like the what you see there. Whereas for methane and ethane, for higher order alkanes, when temperature is around 300 to 400 degrees centigrade, the reaction zones often appear accompanied by a faint blue emission. So this reaction zone appear with a faint blue emissions. Only a small fraction of this reactant with a very small temperature rise up. So this small fraction, only a small fraction of the reactants react with a very small temperature rise. So this is what you refer it to as cool fluids. Because for these low temperatures, we are observing that there is a reaction happening, and your pressure goes down, it cools, pressure comes down, and then again rises up. So this is what you refer to as cool fluids. Now, so the initial conditions, all what we consider were like you had a beaker and you are fully whole reactor mixture is getting ignited simultaneously. But now, when we consider a long duct or a duct of open pipe that you have, and at either one or both of the ends filled with a flammable reactor mixture at a certain temperature. Now when this mixture is ignited at an open end, a combustion, so when it is ignited at an open end, a combustion wave is also called a premixed flame is initiated. So you have a premixed flame being initiated, which propagates. Now this initial flame either can be ignited using an initial piloted ignition, which depends on the magnitude of energy of the source used and the volume of the reactor mixture available. So a minimum amount of ignition energy and a critical volume of this reactor mixture are required for ignition. So these quantities, they depend on your initial temperature and the composition of your reactor mixture. So we'll see how this composition affect the thing in a subsequent time. And once ignited at its open end, a flame steadily propagates it with at a subsonic speed. A flame propagates at a subsonic speed. So when the temperature and reactant compositions are uniform, which is the condition that we are considering here, and the flame propagation depends only on the chemical kinetics that you have. It depends only on the chemical kinetics that you have in the system. So now a flame, so here what you see here, the flame steadily propagates at a subsonic speed, and the hot products of the combustion leave the duct through the open end, now where the mixture has been ignited. So this process is called deflagration, and the propagation speed is called the laminar flame speed. So the propagation propagation speed is called the laminar flame speed. That is represented by SL mostly. Now for most hydrocarbon air mixtures under atmospheric conditions, the laminar flame speed is of the range of 40 to 60 cm per second. And laminar flame speed is the spread at which the flame steadily consumes the reactant mixture. So either you can consider that the flame is propagating or the rate speed at which the unburned reactants are coming towards the flame. So if you write it down, so the laminar flame speed is the speed at which the flame steadily consumes the reactant mixture. So when the reference frame is attached to the flame itself, where the flame is moving and you are sitting on the flame, then it is the speed with which the reactant mixture approaches the flame in the direction normal to it. So you need to remember the word, especially the normal to the flame. So that's very important. Now there are different factors that influence the affecting flame propagation. So there are several factors, and which are like the dimensions of the duct that you have, and the loss of heat, and radicals to the wall, of your duct, and the boundary layer adjacent to the wall. So it is basically the loss of heat to your wall and the boundary layers that you have. And another important thing is the equivalence ratio that you have. Equivalence ratio and initial temperature and pressure of the reactants. So the flame is seen to be curved because of the wall effects. So if you draw the I draw it like this, but actually the flame will be somewhat curved. This is because of the wall effects that you see. So if the dimension of the duct is below a critical value, the heat release due to combustion within the small volume of the duct cannot compensate for the heat loss through the walls in the duct. So, and the flame will not be able to propagate through the reactant mixture. So, if your tube is very small, it will be difficult for the flame to propagate through that, and so eventually the flame will blow off. So, this is particularly used in quenching the flame, or flame flashback and all is emanated based on this principle. Then you were introduced to another particular topic called detonation. Now you saw that in the open tube you had a flame and it was moving out, the combustion products were moving. Now at the same time, if you had a closed end and you ignited the flame somehow here, then at one end of the duct is closed and the mixture is ignited at the closed end, the hot products cannot escape out of the duct. So as a result, the pressure builds up here and the reaction region the pressure builds up between the reaction region and the closed end. So this accelerates the flame, and under certain conditions the flame propagation speed may even become supersonic. So it can move to such high values that it can become a supersonic values. So such a supersonic flame propagation is what you call detonation. Now detonation is not easy to establish in practical situations and finds place in certain unique applications like in pulse detonation engines and all this stuff, where they use these detonation principles to extract the energy to utilize it for producing work. Now some basic differences that were introduced to you for regarding deflagration and detonation were like, for deflagration, say if you had a duct and this is your flame, so you have your unburnt condition here and burnt conditions here. So for deflagration, you saw that the Mach number U1 by C1 was close to 0.001 to 0.03, whereas for detonation this was of the range 5 to 10, so that's what we mentioned as. Then you have the ratio between U2 and U1, it was close to 4 to 6, where it accelerates the thing, but here it is 0.4 to 0.7 in detonation, which means it is a deceleration, where your U1 is greater than U2. Then your pressure ratio, E2 by P1, if you see, this is approximately 0.98 times, that is you have a very slight expansion happening, whereas in detonation you have 13 to 60, 55, so there is a huge compression that is happening within that range. And the temperature ratios, if you see, there were 4 to 16 times there's a heat addition happening, 4 to 16 times, whereas in detonation you have 8 to 21 times the heat addition that is happening. And if you see the density ratios, density ratio is close to 0.6 to 0.25 under deflagration, whereas in detonation it is close to 1.7 to 2.6. So it's detonation, the density ratio also completely changes. Now people start thinking of doing some one-dimensional analysis, and you were introduced to the basic energy forms that you have, that is like mass conservation, which is nothing but ρ1 u1 equal to ρ2 u2 is equal to the mass flux that you have. This is for a steady state condition. Then you have momentum case, where you have P1 plus ρ1 u1 square is equal to P2 plus ρ2 u2 square. And then you have your energy equation, which is nothing but H1 plus half u1 square is equal to H2 plus half u2 square that you have. Then you have the equation of state, which is nothing but P is equal to rho RT that you have. Now based on these things, these particular forms, initially when you are checking with momentum and mass conservation equations, you were shown to a particular form called the Rayleigh line equation. So in the Rayleigh line equation, once you rearrange this mass and momentum, so which I am not going to, since this is explained here, I will write the final equation that you can. So the mass flux square is nothing but the difference in P2 minus P1 by 1 by ρ1 minus 1 by ρ2. So this is your Rayleigh line equation. So using the same procedure, you can get the expression for change in velocity, that is u2 minus u1, which is nothing but your change in flux into 1 by ρ1 minus 1 by ρ2. So this is also one more important relation that you have. Now if you look into the equations, so for detonation, your density at the outlet is greater than your density in the inlet, and the reverse is true for the deflagration case. This is for detonation, and ρ1, ρ2 is less than ρ1 for deflagration, and thus the sign of u2 minus u1, this becomes negative for detonation, whereas u2 minus p1 sign becomes positive for deflagration case. So an expression can be written based on this u2 minus u1 and u2, and finally you can get into form u1 square minus u2 square is equal to p2 minus p1 into 1 by ρ2 minus 1 by ρ1. So substituting the above equation into the energy equation, this equation into the above equation that you have, you get something called Hugoniot curve, or the Chapman-Hugonian relation you will get. So which is found from using the energy equation also into the account. So your H2 minus H1 will now be equal to half U1 square minus half U2 square, which you can substitute now based on this B expression and C expression. You can convert it into 1 by rho 2 plus 1 by rho 1. So for a perfect gas, so in an ideal gas you can either have a perfect or a semi-perfect. So here we are considering perfect gas, where your linear relationship between your H and T is existing, and you have a constant pressure conditions. So at a constant specific heat where R1 equal to R2, the enthalpies can be written as in based on the mass fraction and all. So final thing, the heat addition which is obtained can be written as is as a summation of the mass fraction of the species into the standard heat of reaction minus the summation of over the reactants to EA, the standard formulation of. So there is nothing but products minus reactants, but since it is the heat of combustion, you will have reactants minus products and for this equation. And if you substitute it out, finally your energy equation will finally boil down to a form like gamma by gamma minus 1 into P2 by rho 2 minus P1 by rho 1 minus half of U1 square minus U2 square. Now using this equation, so finally using this equation you can change this U1 square minus U2 square into the Rankine-Hugonian equation form, which is nothing but gamma by gamma minus 1 into P2 by rho 2 minus P1 by rho 1 minus half into. Now U1 square minus U2 square, we have converted it here. So you can write it into that form, that is nothing but P2 minus P1 into 1 by rho 1 plus 1 by rho 2. So this is one more important relation which will help you in solving problems and all. So it's famously called the Rankine-Hugonian curve or the Rankine-Hugonian relation we say. And you got the Rayleigh line from the equation of state that you have plotted here. And now with increase in the mass flux, which eventually results in the slope. So you might have seen the Rayleigh line, how it is being drawn, and what are the slope values, how it changes with change in the equivalence ratio. So if you have a pressure P1 here, and this is your specific volume, which is nothing but 1 by rho 1, and so for the case where your mass flux is approximately 0, you will get a straight line, whereas you will get a vertical line when your mass flux is tends to infinity. And so you have a straight line with a negative slope like this. This is the Hugonian curve, sorry, the Rayleigh line that you have. And if you see here, your Rayleigh line decreases the slope as you decrease your specific volume that you have. And this region A and B are not possible regions. So A and B are the physically inaccessible regions for this particular structure. Then once you have a Rayleigh line in your hand, now you need to go with the Hugonian relations, where you have your pressure at your y-axis and the specific volume, that is 1 by rho on your x-axis, and you have your Rayleigh line. So you have your Hugonian curve like this, and you have your Rayleigh line that becomes a tangent to this particular star. So this particular point is U or T, and the point where it interacts is P, and the point where it interacts See, this is the point C where the horizontal line it intersects, and then you can either have one more line tangent being formed, which is somewhat here. So this will be your point E that you have. Now B to C is not possible because this particular region and this particular region are inaccessible by the Hugonian curve, the Rayleigh curve that you have. So you have V1 for a given V1, and this is your A point that you have. So Hugonian curve is a plot of all possible values of P1 and 1 by rho for a given value of heat. And now you know that B and C are inaccessible region. These are inaccessible regions, and above D is a strong detonation, that is subsonic V2 you have, and between B and D you have weak detonation where you have supersonic V2, and then from C to E you have weak deflagration where you have subsonic V2, and then above E you have strong deflagration, which can have a supersonic V2. So that getting above E and above D are not practically possible because getting a supersonic V2 is a bit difficult. So based on this Chapman-Hugonian curve and Rayleigh line, you have a lot more different things were taught to you and different things were introduced with this particular concept of Rayleigh line and the Chapman-Hugonian curve, and with that you were able to know what are the possible regions, and the point C and E is what you call the lower Chapman-Hugonian point and the upper Chapman-Hugonian point. So said that you saw the velocity conditions and all the stuff. Then you were introduced into some concepts of estimation of the detonation velocity. Then you were introduced into the topic of estimation of detonation velocity. Now in the finally, so it was shown to you that how you need to use your mass equations and solve using the upper Chapman-Hugonian curves and all. I am not deriving that, so it is being shown in your videos. So the final estimation of detonation velocity came with the relation between the density ρ2 by ρ1 is nothing but gamma plus 1 by gamma, and then you had another relation which combines the temperature relations. That is nothing but T2 is equal to 2 gamma square by gamma plus 1 into T1 plus Q by Cp. So this particular two relations are used to find the detonation velocity that you have. So I am not deriving it explicitly because it has been shown already. And said that, then so you were shown how to estimate the detonation velocity that you have. So a detonation velocity, I will just write the formula. You did not need to remember such big thing. So it is nothing but 2 gamma 2 plus 1 into gamma 2 into R2 into your Cp1 by Cp2 into T1 plus Q by Cp2. This is whole to the power 1 by 2. So this was your detonation velocity. Even finally you will be ending up to 2. Then you were shown different examples on how to use the concepts in determining certain values. We will try to solve some examples today. Then said that then you were again later introduced into a concept of laminar flame propagation. So till now we were dealing with where flame was stationary. So steady propagation of a flame through a premixed reactant at a subsonic speed is what we call as deflagration. This is also referred to as a laminar flame propagation. The flame is kept stationary by supplying the reactant mixture at a certain rate, like what you see in a Bunsen burner. So you have your reactants coming at a particular average velocity, then you have a conical flame sitting over here, and then you have a luminous part outside it. So now, such that if the magnitude of the velocity component normal to the surface is taken as the laminar flame speed. So the Bunsen burner conical flame, and there are different ways. You can either have a conical flame or you can have a flat flame over a burner. So different cases were shown to you, and it was shown that for a Bunsen burner flame, wherever you have, say, if you zoom it up, so this is your curve that you have, and this is your vertical velocity, and this is your conical flame cone angle that it makes, and this is your semi-cone angle alpha. So the normal to your flame surface, so this was your flame surface, the velocity normal to this is what is interesting to you. That is what is called the laminar flame speed, and it is nothing but, if U is this, then SL is nothing but U sin alpha that you have. Or you can directly measure it from the volume flow rate, because you estimate the volume flow rate of reactants. So volume flow rate of reactants by the area of cross section can give you the laminar flame speed that you have. Then you were shown that the adiabatic flame temperature versus the equivalence ratio. If you see the adiabatic flame temperature that you get from the theoretically flame temperature that you have. So it can be taken from the equivalence ratio values and the adiabatic that you have. So if you see the curve here, we expect that at equivalence ratio 1 you will be getting the maximum heat release rate and you will be getting the maximum temperature, but that's not true. Your maximum comes at a slightly richer 1.05 to 1.1 range is where you will get the maximum temperature, and this is because it depends on the specific heat conductivity of the reactants and all. So as temperature varies, these things also vary. So this shift in value, so this shift in maximum value is due to dependencies of thermal conductivity or your specific heat or diffusivity, because these all depend at the given temperature in your hand. So it all depends on the temperature. So not at the point where you are having the equivalence ratio 1 is not the point where you are with the maximum adiabatic temperature. Now if you look at the laminar flame speed plot for this particular thing, you will see that there is a close relation between the adiabatic flame temperature and the region layer flame speed. So this tells that the flame speed is a strong function of the temperature that you have. And for normal hydrogen, if you see, it is close to 2.4 meter per second, and whereas for hydrocarbon CH4 and C3H8, this comes close to 1.08 value. And for hydrogen, the laminar flame speed to be maximum at say close to 1.8 equivalence ratio, and the adiabatic temperature will be maximum at say close to 1.07 value. So in short, if I say the premixed flame It depends on your adiabatic flame temperature and the flame speed, laminar flame speed that you have. Now one final thing that I will discuss today is on the topic that was introduced to you was the premixed flame structure. So by flame structure what we mean is the properties or the different parameter values, how they change their values as you progress through a flame. So this is what by flame structure you are. So say you have a tube and you have a laminar flame over here. So if you plot these different parameters that you have, like temperature, concentration or the heat release on your y-axis, and say you have your regions, say this is your reaction region, if you say, and this is your preheat region. Now in this particular case, if you see, initially if you look into the temperature, so initially it was at T0, and as it enters comes close to the reaction region, you will see that there is a slow rise in temperature. Slowly it rises and it reaches the Ti, that is your ignition temperature, near the reaction zone, and it continues the combustion, and it reaches a maximum value of Tf, the flame temperature within the reaction zone, but close to the end you will have the maximum Tf, that is the adiabatic flame temperature. Close to that you will be getting. At the same time, if you see the heat release it slowly increases here, and it reaches maximum when your temperature reaches the flame temperature, and then it comes down and it goes close to zero. Whereas now if you look into the concentration of the reactants, so initially it was having a high concentration, it was here, and then it slowly decreases, and eventually when you are getting the maximum, your concentration of reactants is eventually depleted out. So you get a value of very close to zero. That is, your reactants concentration decreases to very low values when you are reaching the heat of reaction, when you are having maximum heat of reaction. Now there is the flame has certain particular thickness values and all, and once this particular, if your equivalence ratio values are high or low, based on that you can see that there are some more reactions that comes out and happens at the recombination zone that you have outside your reaction zone. So in this zone you will see that if any left out reactants, fuel particles or anything, if it comes out, it will come and it will react in this particular zone and it will produce outcome. So this is the laminar premixed flame structure that was taught to you in week 7. So these are the major topics that were dealt in the week 7. So you saw how a laminar flame structure is dependent on what are factors you need to consider, and how to draw a flame structure, and what is the laminar flame speed, adiabatic temperature, and how to find the laminar flame speed. Then how you find the detonation velocity, then Chapman-Hugonian curve. Then you saw the relation for Chapman-Hugonian curves and the mass, momentum and energy equations. Then difference between your deflagration and detonation conditions, and what are laminar flame and premixed flames that you saw. Then what are explosion limits, and how a H2O2 mixture at a stoichiometric conditions, how to interpret the inverted S curve that you get from the PT curve, and how experimentally you define these different reactors and auto ignition point. So these are the major stuffs that were dealt in the week 7. So said that, now I will move on to the second half of our session, where we will try to solve some problems that we have. So we saw the characteristics of combustion flame and detonation, and we dealt with laminar pre-mixed flames, basic overview of the theory that was covered in week 7. We didn't go in deep, that will take a lot of time. So we wanted to brief, so I wanted to just people to get refreshed with the concepts that you have seen in week 7, and so that you can, when you are dealing with problems, you remember the concepts, where, what and where to apply. So now we will move on to the first question that I have. So the first question is the intensity and speed with which a chain branching reaction takes place. It depends on temperature only, pressure only, temperature, pressure and composition of reactant mixture, or composition of final product mixtures formed. So maybe I wait for 1 or 2 minutes, then I will try to explain. So you can either pause the video or you can wait for 2 minutes. So it's a simple thing. So the intensity and speed with which chain branching reactions takes place, it depends on your temperature, pressure and the composition of the reactant mixtures that you have at your. So your option C will be your answer. So it's just the theory that we learned a few minutes back. Then the next question that I have is the first explosion limit of stoichiometric H2O2 mixture is defined by radical losses to volts depend on hydrogen production because of higher production of OH radicals or due to presence of high quality H2O2. So which could be the reason for first explosion limit of stoichiometric H2O2 mixture? So I will wait for 2 minutes, then I will explain. Please see if you can get answers within these 2 minutes. So the first explosion limit of stoichiometric hydrogen oxygen mixture is defined by the, it is just, you are not, first explosion limit comes after you reach a pressure such that your radical losses to the walls are being worked out. So your answer will be is defined by the radical losses at the two walls. Now if you move on to the next question, the temperature across a deflagration wave, it increases, remains almost constant, decreases slowly, or decreases rapidly. I'll wait for 2 minutes, then please try to guess the answer. I will explain within 2 minutes.
നമ്മൾ സാറിന് അയക്കുന്ന മെയില് ഡയറക്റ്റ്ലി പോയിട്ടുണ്ട് ICSR. ഇതിനെ ഞാൻ കണ്ടായിരുന്നു, മലയാളിയാ, മെസ്സേജ് വെച്ച് കണ്ടതാണ്. അപ്പോൾ അതിങ്ങനെ പറഞ്ഞ് മെയിലും കാണിച്ചു. ഇംപ്രസിന്റെ എന്തോ ഡീറ്റെയിൽസ് ഉള്ള മെയില് 25 ഫെബ്രുവരിയിലൊക്കെ പോയിട്ടുണ്ട്. നമ്മൾ പറയണം ICSR പക്ഷെ അതിനെക്കുറിച്ച് 2 പ്രാവശ്യമായിട്ട് ഇങ്ങനെ വരുന്നുണ്ടത്ര. അതെ, മൈക്രോഫ്ലൂയിഡ്സിലുള്ള ഒരു പ്രൊഫസർ ആശിഷിന്റെ കൂടെ വർക്ക് ചെയ്യുന്ന സുജിത്ത് എന്ന് പറഞ്ഞൊരു ചെക്കനുണ്ട്. ആ ചെക്കൻ്റെ മെയിലിലേക്ക് നമ്മൾ സാറിന് അയക്കുന്ന മെയില് ഡയറക്റ്റ്ലി പോയിട്ടുണ്ട് ICSR. ഇതിനെ ഞാൻ കണ്ടായിരുന്നു, മലയാളിയാ, മെസ്സേജ് വെച്ച് കണ്ടതാണ്. അപ്പോൾ അതിങ്ങനെ പറഞ്ഞ് മെയിലും കാണിച്ചു. ഇംപ്രസിന്റെ എന്തോ ഡീറ്റെയിൽസ് ഉള്ള മെയില് 25 ഫെബ്രുവരിയിലൊക്കെ പോയിട്ടുണ്ട്. നമ്മൾ പറയണം ICSR പക്ഷെ അതിനെക്കുറിച്ച് 2 പ്രാവശ്യമായിട്ട് ഇങ്ങനെ വരുന്നുണ്ടത്ര. എന്നിട്ട് ICSR റിപ്ലൈ കൊടുത്തു, ഞാനെല്ലാം നമുക്ക് റിപ്ലൈ കൊടുത്തിട്ടുണ്ട്. ആ മെയിലിൽ ജഗന്നാഥ് റിപ്ലൈ കൊടുത്തിട്ടുണ്ട്. ആക്ച്വലി അത് ശ്രദ്ധിച്ചിട്ടുണ്ടോന്ന് എനിക്ക് അറിഞ്ഞൂടാ ആരെങ്കിലും. എന്തോ ഇതിന്റെ മെയിൽ ID സുജിത്ത് 998 എന്തോ അതിന്റെ മെയിൽ ID. അത് ഡയറക്ട്ലി ടു പോയേക്കാം, CC പോലും അല്ല.
Yeah, so temperature across a deflagration wave, so it's direct. So what we have discussed, it increases. So temperature across a deflagration wave, you have the unburnt reactants getting ignited, and once it ignites, your temperature starts across the wave, it increases. Now the next question I have is, the velocity across a detonation wave, will it remain constant or increase or decrease or increase gradually? So you can think for 2 minutes and I will let you. So the velocity across a determination wave, will it remain constant, increase or decrease, or increases gradually? So you know, as of our determination wave, you have the closed chamber and you ignite it up here. So your pressure over here increases, so which eventually means the velocity across a detonation wave will eventually decrease. Now if you move on to the next question. So for a railway line drawn from a given initial state P and nu1, its slope decreases as the mass flux decreases, heat is added, or the mass flux increases, mass flux remains constant. So maybe I'll wait for 2-3 minutes for you to think of it, and then I will explain it. So when you are drawing this railway line, we show that when your mass flux is close to 0, you have a horizontal line, and your mass flux is close to infinity, you will have a vertical line for your stuff. Then you have your line. Now when your mass flux is here, you have a higher slope, and as you decrease your mass flux, that is, you are coming from infinity to 0, that is, your mass flux is decreasing, you will see that your slope is decreasing. So its slope decreases when the mass flux decreases. That is the case where you will have your slope decreasing. Now if I move on to the next question. As the mass flux is decreased, the railway line would tend to be at 45 degrees, vertical, horizontal, or at 60 degrees. This I think you can give the answer within 2 minutes. So I will wait for 2 minutes. Then I will let you know the answer. as discussed. So in the earlier part, I have shown how when your mass flux is decreasing, how you grow from infinity to zero. So your A and B are inaccessible regions. So the question was, as the mass flux is decreased, the Rayleigh line would tend to be at 45 degrees vertical, horizontal, or at 60 degrees. So you will have this and you have your line. So as it decreases down, you can see your mass flux was infinity and it comes close to zero. So your mass flux eventually comes to a horizontal line. As your Rayleigh line would tend to be close to horizontal line as your mass flux is decreased. So your answer will be C, which is horizontal. Now if we move on to the next question. The Mach number at the lower Chapman-Jugonian point is subsonic, supersonic, equal to 1, or it is undefined. So I'll wait for 1 or 2 minutes for you to get the answer. So the Mach number at the lower Chapman-Jugonian point will. So we saw that if you have a line and you have your Jugonian curve there and you have your tangents being drawn, the lower Jugonian point E. So above that you have your supersonic velocities and below that you have your subsonic velocity. So your E point, that is your lower Chapman-Jugonian point, will have a Mach number, that is distribution between the subsonic and supersonic. So it will have a value equal to 1. So moving on to the next question. So this is a numerical. So where a combustion wave propagates with a mass of 120 kilogram per meter square second. Unburned gas is at 1 bar and 298 Kelvin. The molecular weight and the specific heat ratio of the mixture burnt and unburnt are 32 kg per kilomole and 1.2 respectively. If density decreases by 5 times, final pressure in Pascal is what the question is. So maybe I'll wait for 5 or 6 minutes for you to try it out. Then later I will explain the answer. Okay, so I'll try to show you. So your mass flux is given as 120 kilogram per meter square second. Then your initial pressure P1 is given as 1 bar and your temperature is given as 298 Kelvin, and the molecular weight is given as 32 kilogram per kilomole, and your gamma is given as 1.2, and additionally it is given that P2 is P1 by 5, and they are asked you to find what is the P2 in Pascal. So we know from the Rayleigh line that mass flux square is nothing but P2 minus P1 by 1 by rho 1 minus 1 by rho 2. Now P2 is what you need to find. P1 is given to you 1 bar. 1 bar is nothing but 101,325 Pascal divided by 1 by, now you need rho 1 and rho 2 is needed. Sorry, here it is rho 2 is given as rho 1 by 5. Now you need either rho 2 or rho 1, but you know pressure and temperature. So from equation of state, which is nothing but P equal to rho RT, you can get rho is nothing but P by RT, and so here 1 you can put. Pressure at 1 bar is 10325 Pascal, and R is nothing but universal gas constant by molecular weight. So for rho 1, your molecular weight is given as 32 into temperature, that is 298 Kelvin. Now if you substitute it here, you will get a value close to 1.2915 kilogram per meter cube. Now you know rho 1, so you can get the value of rho 2 is something but rho 1 by 5. So if you substitute it here, now your mass flux is given to you. So mass flux is given as 120 kilogram per meter square second, which is equal to P2 minus 101,325 by 1 by 1.2915 minus 1 by rho 2 is nothing but 1.2195 by 5. So this implies P2 is equal to 55403.398 Pascal. So P2 Pascal. So you can either write it in kilopaskal, but your answer is asked in Pascal. So 55403.32, so which is close to 55404. So B option is the correct answer for this. I hope that is clear. Now if we move on to the next question. So in problem 8, the Mach number of unburned gas is what, and change in velocity across the combustion wave in meter per second is what. So there are two things that you need to find: the Mach number of the unburned gas and the velocity across the combustion wave in meter per second. So I will wait for 5 minutes. You can try it out. we are able to get to the answer. So you are asked to find the velocity of unburnt gases. Which is nothing but mass flux of unburnt gas by the density of unburnt gas. So mass flux is given as 120 is given to you, and density of unburned gas we determined 2.15985. So it will come to 92.909 meter per second. Now you are asked to find the Mach number. So Mach number is nothing but velocity by speed of sound. Now you need to know the speed of sound here. C can be written as gamma t, and gamma is given as 1.2, and R is nothing but 8314 by 32 because it's unburnt is given, and a temperature of 298. So your C comes to 304.809 meter per second. So your Mach number will be 92.909 by 304.809. So this comes close to 0.3048. So this is the Mach number of the unburnt gas that you have. Now you are asked to find the change in velocity across the combustion wave. So which is nothing but U2 minus U1, which is nothing but mass flux into 1 by rho 2 minus 1 by rho 1. So mass flux, you know, it is 120 into 1. Rho 2 is nothing but rho 1 by 5 minus 1 by rho 1. So this is nothing but 120 into 5 by rho 1 minus 1 by rho 1. So which is nothing but 120 into 4 by rho 1. So this is 120 into 4 by rho 1 is nothing but 1.29158. So this comes close to 371.637 meter per second. So this is your change in velocity across the combustion. So your answer will be option C, where your Mach number is 0.035 and your change in velocity across the combustion wave is 371.60. So your answer will be option C. So I hope it is clear. Now if you move on to the next question. In problem 8, the heat released in kilojoule per kg is what they are asking, and temperature of the burnt gas in Kelvin is, and the Mach number of burnt gases. So now they are asking the values for the burnt conditions. So I'll wait for 5 minutes, you can try it out. since we are asked for heat release rate, so your equation Q, we know it is nothing but gamma by gamma minus 1 into P2 by rho 2 minus P1 by rho 1 minus half into U1 square minus U2 square. Now U2 minus U1 is, we know it is 361.3673. So from here U2 is nothing but 371.637 plus 92.905. So you get close to 464.546 meter per second. So now you got U2 and you know U1, rho 1 and rho 2 you know, P1. So now all the values you know. So Q, if you substitute, which is 1.2 by 1.2 minus 1 into 55403.398 into 5 by 1.21958 minus 10 to the power 5 by 1.21958 minus half into U1, that is 92.909 square minus 464.546 square. So your Q value will be 925,913.0971 joule per kg, which is approximately 925.913 kilojoule per kg. So this is the heat released in kilojoule per kg. Then they are asked to find T2. So T2 is something but P by rho R, which is nothing but P2 by rho 1 is into Ru by molecular weight. So P2 into molecular weight by rho 2 into Ru. Now P2 is nothing but 55403.398 into molecular weight 32 into 5. That 5 comes from the rho 2 case, which is nothing but rho 1, 219158 into 8314. So if you substitute here, you will get a value close to 825.515 Kelvin. So this is the burnt temperature T2 that you are having. Now Mach number, you know it is nothing but U by C, and you got U1, which is nothing but 464.546 by C is nothing but gamma RT, that is nothing but 1.2 into 8314 into by the molecular weight for burnt gas is 1.2. Burnt and unburnt is given as 32, so we can write it 32 here into the temperature that you got, which is 825.15515. So if you substitute here, you will get value as 0.91568. So this is your burnt Mach number of the burnt gas. So you got 925 joule per kilogram Kelvin, that is your first, and 825.515, that is this, and 0.916, this is this. So your correct option will be option D. So I hope that is clear. Now if we move on to the next question. Due to detonation wave propagation through a stoichiometric mixture of methane and oxygen, initially at 0.4 megapascal and 298 Kelvin, forming hot water, where heat released is 13.4358 megajoule per kilogram water. Density increases by 2 times of the initial value. Ratio of specific heats is 1.4. Density of unburnt and burnt mixture in kilogram per meter cube R is the question. So maybe I'll wait for 2-3 minutes. You can try it out. Then I'll leave it. Here you have methane plus oxygen given, and you have been given the pressure P1 as 0.4 megapascal, and you have your temperature as 298 Kelvin, and your heat Q is nothing but 13.4358 megajoule per kilogram of water is given, and you have been given that density increases by 2 times, and your gamma is given as 1.4, and we are asked to find the unburned and burned densities. Now from the methane equation, that is CH4 plus 2O2 gives rise to CO2 plus 2H2O. The mole fraction of methane, if you see, which is nothing but 1 by 1 plus 2, which is 1 by 3, is nothing but 0.33, and the mole fraction of O2, if you see, which is nothing but 1 by mole fraction of methane, which is 0.667. So your molecular weight of mixture is nothing but the sum of mole fraction into molecular weight of the total thing, that is nothing but molecular weight of methane into mass fraction of methane plus molecular weight of O2 into mass fraction of O2, which is nothing but the mass fraction of molecular weight is 16 into mass fraction is 0.33 plus 32 into 0.667. If you do, you will get close to 26.672 kilogram per kilomole. Now why we want the mixture molecular weight and all, we will see. So the density of unburned gases is nothing but pressure of at unburned by R into T at unburned, that is nothing but pressure into molecular weight of the mixture by universal gas constant into T. So unburned pressure initially is 0.4 megapascal, so it is into 10 to the power 6 into molecular weight, that is 26.672 divided by 8314 into temperature 298. You will get close to 4.306 kilogram per meter cube. Now density of burnt gases is Pb by Ru into Tb. Now Pb into molecular weight of burnt gases by Ru into T. And it is given that the density of burnt gases is 2 times the density of unburned. So it is nothing but 2 times 4.306, which is nothing but 8.6123 kilogram per meter cube. So this is for unburned and this is for burnt. So your answer will be option A, where you have 4.31 and 8.62 as your answer. Now a continuation to this, in problem 11, the pressure across the detonation wave, the pressure across the detonation megapascal is they are asking. So here you know the heat release equation, that is gamma minus 1 P2 by rho 2 minus P1 by rho 1 minus half into P2 minus P1 into 1 by rho 1 plus 1 by rho 2. Now if you substitute the values here, that is 1.2 minus 1.1 into P2 by 8.623 minus 0.4 into 10 to the power 6 by 4.306 minus half into P2 minus 0.4 into 10 to the power 6 into 1 by 4.306 plus 1 by 8.6232 613 if you do. So your heat Q is given as 13.43 into 10 to the power 6, which if you substitute here, you will get 0.406 P2 minus 3257 27.726 minus 0.174 P2 plus 69600. So if you solve it out, you will get P2 close to 58944.50.8, which is approximately 58.944 megapascal. So this is close to 59 megapascals that you have. So the correct answer will be option C, which is 59 megapascals. So I hope that is clear. So yeah, so we have reached the end of today's session. So we have seen different problems on how to deal with characteristics of combustion flame and detonation, and what are linear flame, laminar pre-mixed flames, and how to find the different properties of a flame. So we will meet in the next session. We will deal with more details on the different types of combustion processes in the next week. So have a good night and thank you.